Today we're going to extend our library of functions. So far we've talked about the absolute value function, and we've talked about the lower degree polynomial functions. They're all very useful, but over the course of hundreds and hundreds of years, scientists have worked out there's a whole, well, probably about 5 or 6 families of functions that have proved to be useful. And so we're going to now go through those other families as well. And the first family that we've got are the exponential functions. So an exponential function, I'll say this whole thing is important. So an exponential function is a function of the form some number times another number k to the x, where k is another number. So the variable is in the exponent. Right? When we had a polynomial function, it was x squared or x to the power 1. Here it's something to the power x. Okay, that's what makes an exponential function an exponential function. The variable is in the exponent. Now the other thing is, we're only ever going to consider bases that are positive, and we're not going to have b equal to 1 because 1 to the any power is just 1. Right, so 1 is a special case in that case. So this is our definition of an exponential function. And a very simple example of an exponential function is f of x is 2 to the x. So in this case, a would be 1, b would be 2, and k would be 1 in here. So this one has a is equal to 1, the base is 2, and the k is also 1 in that particular function there. Now we want to determine, this says determine the domain and range of this function. So by domain we mean for what values of x can we calculate the function. So for what values of x can we calculate 2 to the power x? And if you think about that for a little while, it's not actually immediately obvious, I don't think. For some numbers it is. So for example, if x is a counting number, if x is a counting number, then we don't have any problems calculating the value. So for example, here I could say function 3. I can calculate 2 cubed because that means 2 times itself 3 times. So 2 times 2 times 2. So function 3, or 2 to the 3, is 8. So there's no problems whatsoever calculating the function when x is a counting number. No worries there. What happens if we go beyond that and we go to the whole numbers? So if x is, to use the maths speak on you, if x is an integer. So for example, if I had to calculate f to the minus 3, f minus 3. So what's the function value when x is equal to minus 3? So in here I have to calculate 2 to the power minus 3. Now, a little while ago, we actually, way back in the algebra section, we talked about the laws of arithmetic, and as part of that we had the index laws. And you remember your index laws well now, I hope. And you would recognise, yeah you do, don't you? Okay. A slight bit of humour from out the front here. Okay. But if you go back to your index laws, 2 to the minus something was interpreted as 1 on 2 cubed. And so I can do that because I know 2 cubed, that's 8. So this function value therefore is 1/8. So can I say to you, here with exponential functions, you're going to be using your index laws a lot. I think I gave you 7 of them. It would be good if you wrote them down and had them somewhere near you at some stage. Okay, that would be a good certainly a good thing to have on your cheat sheet, I would imagine. Okay, so we can definitely, so all the counting numbers, all the integers are definitely in the domain of this thing. What happens if we go beyond that and say if x is a rational number. So if x is I'll just say if x is rational. So an example of a rational number, i.e. the ratio of whole numbers, would be something like 3 on 2. So if I've got a fraction, can I calculate the function when I have x being a fraction? And again, whip out those index laws. Here I have 2 to the power 3 on 2. And I can interpret that as 2 cubed all to the power a half. Or I could have said 2 to the half all cubed. It didn't matter which way around you do it, you'll get the same answer. Now 2 cubed is 8, so that's 8 to the half. And we interpreted our fractional power up here as being the square root. So that would be the square root of 8, which I guess if I wanted to I could write as 2 root 2. So function 3 on 2 is 2 root 2. And I can do that for every rational number. I can split it up into a 1 on and a whole number, and so I can work out the value of the function when x is a rational number. So far this is looking good. There hasn't been any values of x for which we can't calculate f of x, but there's one more case to go. And what if x is irrational? So for example, imagine I was trying to calculate the function value when x is the square root of 2. Certainly I can write down what it should be. It's 2 to the power of the square root of 2. But what does it mean to have a power of the square root of 2? I mean, up here we interpreted 2 cubed as 2 times itself 3 times. So that had an obvious interpretation. This doesn't. This doesn't have an obvious interpretation. But we can actually calculate this value. And the way we do it is this. So I'll say note that, now, being an irrational number, the square root of 2, its decimal representation goes on forever without repeating. So I can actually write down some approximations to the square root of 2. For example, I can say the square root of 2 is approximately 1.4. Now that's not exact because I've left out the infinite number of other decimals sitting in there. But that's not a bad approximation. And this being 1.4, I can say therefore function square root of 2 is approximately 2 to the power 1.4. And that one I can calculate, because 1.4 is the same as 14 on 10. And so I can say that's 2 to the power 14 all to the 1 on 10. So the 10th root of 2 to the power 14. And I can't do that in my head, but my calculator can. And it got something like 2.639 to 3 decimal places in there. If that answer isn't accurate enough, well, I can say, well, the square root of 2, a little more accurately, is 1.41. And so therefore the function value is 2 to the 1.41, which is 2 to the 141 on 100. And that's 2 to the 141 all to the 1/100th. And when I do that, I get something that's about 2.657. And I can keep on getting the square root of 2 as accurate to as many decimal places as I like, and hence I can work out my function to any accuracy that I like. So even though I haven't got a nice, easy interpretation of what 2 to the power of the square root of 2 is, I know what the value is. And so in other words, I can calculate this function for any value of x. So after all of that, we've decided the domain is a set of all real numbers. Okay, but it wasn't an easy path. So let me just write down what I just said there. So this implies that we can calculate and calculate function square root of 2 to as many places as we want. And so our conclusion out of all of that is that the domain of this function is I can calculate the function value for any real number. And that will be true of all exponential functions. All exponential functions will have a domain of all real numbers. Having calculated the domain, I now need to work out the range. And while we might be able to do it just by looking at it, it's probably not a bad idea just to draw the graph, and that'll show it to us. So let's have a look at the graph of 2 to the x. So I'm going to draw it there, but I'm going to do a bit of working first. So if I'm drawing the graph, I said to you on Tuesday, there's some good points, some good information that will help us draw it. And the first thing was the domain, and we've now got that. So it's a set of all real values. We then said, okay, well, what's the y-intercept? That's always a good thing to know. And the y-intercept is the function value when x is equal to 0. So function 0 is the y-intercept, and that's 2 to the power 0. And according to our index laws, 2 to the power 0 is 1. So the y-intercept in this case is 1. And so as I draw my graph, I can come up to here and say, look, I know it cuts the y-axis at 0, 1. So I know it passes through that point. Sitting there, it passes through 0, 1. So there's my first piece of information. The x-intercept is a good thing to know. X-intercept or intercepts. Now, that will be when my function, so it's the x value when f is equal to 0, which means I have to solve the equation 2 to the x is equal to 0. And I guess here it takes a little bit of thought. But clearly if I'm squaring, cubing and so forth, 2 to the x is going to be large. So that's not going to be 0. If I put in negative values of x, this becomes 1 on. And so I get a half, a quarter, a third, a 16th and so forth. So in fact, this has no solution. There is no value of x that makes that true. This has no solution. Sitting in there. So this graph never cuts the x-axis. And here, that's what that tells us. So I'll actually write that in I. Graph doesn't cut the x-axis. Is this function odd or even? So we have a check. Is it odd or even? So we look at function minus x. Function minus x is 2 to the minus x. 2 to the minus x we would interpret as 1 on 2 to the x. That's not function x, so that means it's not even. And if I have a look at minus function x, that is minus 2 to the x, and it's not equal to that either. So that tells me that it's, this says not even, and in this case it's also not odd. So there's no symmetries present in the graph. So unfortunately that doesn't help us in this case. And the last thing, because we've got a domain of all real numbers, there won't be any asymptotes, so I don't have to do that. So my last piece of information is this long-term behaviour. So the long-term behaviour, I want to look what happens as x gets very, very large positively. So I say as x goes towards infinity, what does the function do? Well, it's 2 to the x, so let's put some values in. 2 to the 10, what's that? 1024. 2 to the 100, who knows? Big, right? And the bigger the power, the bigger the number. Always positive, so f goes off to infinity. The other possibility, of course, is that x goes towards minus infinity. And we saw here that a negative index was the same as 1 on. Now, as x gets very large, like minus, if I put minus 100, this becomes 1 on 2 to the 100. That number is really, really big, 2 to the x. So 1 on 2 to the x is really, really small. So that means f gets closer and closer to 0, but it's always positive, so it's coming from above. And so if we go back now and put all the pieces together, I mean, I'll put another couple of points on here. I know that when x is 1, function will be 2. 2 squared is 4, so they're easy points to put on. And I'll just turn this upside down for a bit. So this thing will come down like that. And there will be your graph of function x is equal to 2 to the x. So I'd say this is the graph of y is equal to 2 to the x. And so that characteristic shape is what all exponential functions looks like. And probably the most common application you would have seen of exponential functions is to populations. You know, populations grow exponentially. It means they grow like this. Okay. Interestingly, just to use some math speak on you, you can see here that y equal to 0 is a horizontal asymptote in this case. The graph gets down and gets closer and closer to y equal to 0, but it never actually reaches it. So we call that a horizontal asymptote. The other thing that's very important to realise here, I mean, it's obvious, but let me state it anyway. What happens with an exponential function is every time I increase the x value by 1, the function value doubles. So from here, as I get x from 0 to 1, the function value goes from 1 to 2. As x goes from 1 to 2, the function value goes from 2 to 4. So the function is increasing by a factor of 2. So let me say that. I'll say note, as x increases by 1, function x equal to 2 to the x, I'll say doubles, or increases by a factor of 2. You multiply by 2. Compare that to as x increases by 1. If I had f of x is equal to 2x, our linear function, what happens there is that the function increases, f of x increases by the value 2. So in this case, so here, this one you're actually multiplying by 2 every time. This time you're adding 2 every time. So as a result, exponential functions get big way quicker than linear functions. Okay? It's because one's a multiplicative factor, the other one's an additive factor. Is
that relative to the 2 functions?
That's right. If that had been 3 to the x, it would increase by a factor of 3. Yep, that's right. So it's the base that determines the actual factor there. Yes. So, out of all of that, I actually forgot to give you the range. Let me now... I went through all of that and I didn't even get the range out of it. You can see the range here though. So the range is the set of y values such that y is greater than 0. It doesn't ever reach 0, but for every other value there's a point that has that as a y, has those y values. And so for all of our standard exponential functions, the domain is set of all real numbers, the range is the set of positive y values. Okay. So, we managed to revise what we did last lecture in here, or part of it. Now I'm going to revise the other part of what we did last time. Because it says here, sketch the graph of function x is equal to minus 2 to the x. And if you remember last time I said to you, if you know the parent function, sometimes we can apply some nice transformation to get the graph of the next one. So in this case, so here in part A, I can say the graph of function x equals minus 2 to the x is the graph of the function that I already know, y equals 2 to the x, and because it's minus, it's reflected in the x-axis. So given that I know one, I can produce the graph of the other one. So if I can just quickly... Okay, so that's the graph that I know. That's y is equal to 2 to the x. So the graph I want will come down here. And it will be its reflection down there. So that will be the graph of y is equal to minus 2 to the x. It's its reflection in the x-axis. Part B, it's not so obvious there what that graph should be. So we're just going to resort to common sense. Don't know if that's a good idea or not, but we'll try it. So this is saying, if I put x equal to 1 here, function 1, that'll be 2 to the minus 1. That'll be the same as what's happening in the graph of 2 to the x when x is minus 1. So what's happening in that graph is what's happening in this graph here. So what I'm going to do, so that is what happens at 1, this is what happens at 2, so that will be there. What happens there is the same, what happens here is here. So what I end up doing, because this is minus x here, is I end up reflecting in the y-axis in here. So the graph of 2 to the minus x actually goes this way. Like that. So that's the graph of 2 to the minus x. And I guess down here, just let me point out that 2 to the minus x is the same as 1 on 2 to the x. So those two graphs, those two functions are the same function, just via our index laws. 2 to the minus x is the same as 1 on 2 to the x, which is the same as a half to the x. Sitting in there. So there's some of our graphs sitting in there. And I guess I'm expecting that if I were to give you a version of these things, you would have an idea of what it looks like qualitatively. So if I said to you it's an exponential function, you'd know it goes like that. If it was e to the 2 to the minus x, you'd know it goes that way. Okay? Your cheat sheet is getting fairly full at this stage. But I would say to you, for all of the main functions that we look at, you should have an idea of what the graphs look like. So far we've been working with 2. The same sorts of things happen with 3. So I won't actually go through the details, but with 3 to the x, so here in part A, with 3 to the x, again the y-intercept is 1, but this time it increases by a factor of 3. So this will be down here at a third. And so let me come around and do this. So this is much, much steeper. Down like that. That would be the graph of y is equal to 3 to the x. It has the same shape as 2 to the x. It's just steeper. And in fact, I could put on here 2 to the x because it would go there and there. And so 2 to the x, if I were to draw it, would look like this. So that would be y is equal to 2 to the x. Same basic shape, just that when I have a larger base, the graph is steeper, gets quicker, gets bigger quicker. So something like 10 to the x would be very steep. But as I say, all exponential functions have that same basic qualitative shape. So in part, you can see here again, the domain is the set of all real values. The range is the set of y values greater than 0 in there, same as before. Let's look at this one. Here, the graph of f is equal to 3 to the x plus 1. Now, in that case, in here, let me just scribble over here for a bit. If I have function x is equal to 3 to the x, then function x plus 1 is everywhere I see x, I have to put x plus 1, so that's 3 to the x plus 1. And we said last time that the graph of function x plus 1 was the graph of function x shifted to the left by 1 unit. So the graph of f is equal to 3 to the x plus 1 is the graph of y is equal to 3 to the x shifted to the left by 1 unit. So if I do the graph of 3 to the x, which is going to look something like that, then all I have to do is move it across 1 unit. And it's going to go like that. That's y is equal to 3 to the x. Here's y is equal to 3 to the x plus 1. Okay, so let's have a look at some uses of the exponential function. I say here boldly, exponential functions have many applications. They do. So here's one. It says, after the accident in 1986 at the Chernobyl nuclear reaction, large amounts of a radioisotope escaped in the atmosphere. Immediately after the accident, the level of this isotope was 10 times what it should be, the safe level, given that the half-life of this isotope, 131, is 8 days. So that's the critical bit in here that we need. It says, would the levels have fallen to a safe level after 32 days? Now, we're going to try and write down an equation that tells us the levels of the isotope in the atmosphere. So let's start off by saying that. So let the concentration of this isotope, 131, after T days be, and I'm just going to call it capital C, C for concentration, and it's going to vary over time, so it's a function of time. Now, a half-life means that over the period of 8 days, the amount of this stuff here, the concentration of it, will have decreased by a factor of 2. The important thing is there, decreased by a factor. As soon as you see that, you think exponential function. All right? So, in here, half-life means this thing decreases by a factor of 2. So therefore, the kind of function that I'm going to use to describe this concentration is going to be an exponential function with a base, if you like, of a half, because it's decreasing. Not going up by a factor of 2, it's going down by a factor of 2. So I can say here, so let CT be A times a half to the K times T. And what I need to do is find suitable values of A and K to fit the information that we've been given here. So now what I'm going to do is I'm also going to, a half I can write as 2 to the minus. So that function and that function are the same thing. And you'll tend to see it as 2 to the minus KT most of the time. So I'll write it that way as well. But as I say, it's exactly the same thing as a half. And here my job is to find suitable values of A and K. Now, it hasn't told me what the safe level of this isotope is, so I'm just going to call it this. So if the safe level is, and I'll just go CS, safe concentration level, because I can't think of anything better to call it. If that's the case, then we know. Then we know this. We know that at t equal to 0, which we will take as being when the accident actually happened, the concentration was 10 times the safe level. That's part of what we've been told here in the question. It was 10 times the safe level. So whipping that into this formula here, it says when t is 0, c is 10s. So therefore I have 10 cs is equal to A times 2 to the minus, now k times 0 is 0. 2 to the 0 is 0, So that right-hand side is just A. So A is 10 CS. So now I have a suitable value for A. It's 10 CS. And it seems fairly clear, I think, that this A will always be the value of your quantity at the beginning. It'll always be that. So anyway, so now I have, that tells me that my function is 10 CS 2 to the minus kt, and all I have to do now is find k. Found A, got to find k. And this is where I get to use the half-life bit. I've used the fact that it told me something about the half-life to guess the base, but now I actually use the actual period here, the half-life is 8 days, to determine the k. So I know, here I can say, since half-life is 8 days, that says at t equal to 8, after 8 days, the concentration is a half of what it started with. A half 10 CS. So in other words, 5 CSs if you like. So I have 5 CS is equal to 10 CS 2 to the minus k times 8, because t is equal to 8. I can actually divide both sides by CS, so it doesn't matter what the original level was, that disappears. And now I'll have here 5 on 10 is equal to 2 to the minus 8k. I'm going to write that here as, I'm going to write the 2 to the minus, I'm going to write that as a half 8k, and on this side I'll write that 5 on 10 as a half as well. And if I say that's half to the power 1, you can see that for the left-hand side to equal the right-hand side, 8k has to be equal to 1. That's the only way a half to the 1 can equal a half to the 8k. So this tells me that k is 1 on 8. It's 1 on the half-life. Yeah. And so I get my nice formula. So I can say thus, because that makes me sound smart, as I always say. So CT here, here's my equation. It's 10 CS 2 to the minus 1 on 8. So I'll just write that as T on 8. And there is an equation describing the concentration of this isotope. And in fact, what I would probably say is here's an exponential model of the concentration. It's not 100% accurate. This thing's probably not exactly 8 days, but it's a good approximation. So, up here it said, would the levels have fallen to a safe level after 32 days? So it says, what will the concentration be when T is equal to 32? So lastly, I can say now, C32 is 10 CS 2 to the power minus 32 on 8. And you can see why we chose 32, because it happens to be easy. 32 on 8 is 4. So this is 10 CS 2 to the minus 4. 2 to the minus 4 is 1 on 2 to the 4. So this is 10 CS 1 on 16. And so here I've got 10 on 16 CS. So after 32 days, the concentration has dropped to 10/16 of CS. CS was a safe level, so this is smaller than the safe level. So this says, yep, after 32 days we're safe. So therefore, I probably should say that's less than CS in there. So therefore, the level is safe after, or not after, but at 32 days. So there's a fair bit of work in that. It requires a fair degree of proficiency with your index laws. Right? I quite happily swapped the minus around all over the place as it suited me in each of these things. That, I think, takes some practice. The concept's simple. I'm just manipulating this, but actually doing it takes some practice, I think. So I've tried to actually say in general, if you're looking at a quantity, be it concentration of isotopes or whatever, if it increases by a given factor every time period, then we use an exponential function with b as the base. And so what we did there, this is just saying you can always do it. Okay? The process that we followed there works in general, not just for things that are half-lives. But having said that, nearly all the examples we give are half-life ones. So, anyway, but it holds in general. And as I say, here's another example, and it's a half-life example. So, given that the carbon-14 has a half-life of 5,730 years, what would be the percentage? As soon as you see half-life, you think to yourself, I'm going to use an exponential function with a base a half, or if you like, base 2 to the minus, whatever. So let's set up some variables. Let the amount of carbon-14 in a body after time t in years b, and we'll go n. I don't know why we chose an n, maybe because I put it up there. Then again, our model will be n of t will be a half to the kt, which we can write as a 2 to the minus kt, where we have to find suitable values for a and k. A and k to be found. In here, carbon-14 has a half-life of 5,730 years. What's the percentage of the original amount would be remain after this many years? Again, we don't know the original amount, but it's not a problem. I'm just going to call it something. So I can say, if at t equal to 0, the amount of carbon-14 is, and I'll just go n0 because I don't know what it is, then we can see that. Now, I don't know, am I doing the right thing here? I might put it here. Then A is equal to n0 is the thing. So that tells me that my function that I want to use to describe the amount of carbon-14 is an exponential function n0 2 to the minus kt. You can see that when t is equal to 0, 2 to the 0 is 1, so n is equal to n0, which is good. My next job is to find k. And I'm told that when t is equal to 5,730, the amount is half of what we started with. So I can say at t equal to 5,730, n is equal to a half of n naught. So in here I have a half n naught is equal to n naught t to the minus 5,730 k's. Your n naughts cancel out. And I'm going to write this 2 to the minus here as a half. And so I have 5,730 k's. Over here I've just got half to the power 1. So that tells me, I can say equating exponents is what I'm doing. Equating exponents tells me that 5,730k is equal to 1, i.e. k is equal to 1 on 5,730. So in these things with the half-life, k always turns out to be 1 on the half-life. It'll always be that way. And so my model is nt is equal to n naught 2 to the minus t on 5,730. This particular question says, what happens when t is 2,865? All I have to do is evaluate my function when t is 2,865. So n at 2,865, and again you'll see that the choice of that number was so that this arithmetic here turns out nice, because 2,865 happens to be nicely a half. So this is n naught 2 to the minus a half. 2 to the minus a half is 1 on 2 to the half. So that's 1 on root 2. So this becomes n naught on root 2. So that's the amount that is left. How does that compare to the amount we started with? Well, what's the ratio of those? So I can say here, I'll say here. So the percentage remaining at t equal to 2,865 is, it's n naught on the square root of 2 divided by n naught times 100 over 1. That's my percentage. And that's about 100 divided by the square root of 2, which turns out to be around 70.7. So the percentage remaining is about 71%. And you can see in here, all the while, I'm assuming that you are good at manipulating these things. So all those things we talked about in the first couple of weeks, doing the algebra, modifying expressions, etc., I'm assuming you're good at that now. Okay? I'm hoping you were good at that. Because I'm just flying over that like it's easy. And yet I would say for most people, most of the mistakes they make is not in not being able to understand this, it's actually doing the algebra. So you're actually falling down not because of your lack of understanding of this stuff, but of the stuff that's gone before. And perhaps not even lack of understanding, it's probably just lack of practice, I would suggest. Before I get going again, I was just asked a very good question, and so I thought I'll repeat it for all of you. Now I may end up confusing you more than I already have, but let me try and say it anyway. You don't yes, you can't get much lower than 0, you think? Okay. But the question was, having got a function of this form, for example, c is equal to a2 to the minus kt, what are the a and the k? What am I actually doing with that? And the answer is this. We've decided in these particular half-life questions, because the quantity is changing by a given factor, that we're actually going to use a exponential function. And an exponential function with a negative index, the graph goes something like this. Right? So it decays and gets closer and closer to the x-axis. By changing the a and the k, what we're doing is we've still got an exponential function, but changing the a moves the graph up the axis. Changing the k can make it flatter or steeper. So what we're doing by choosing suitable values of a and k is choosing a suitable form of the exponential function that matches the situation that we've got, that we're looking at. If the half-life is long, this thing will be up like this. If the half-life is short, it'll go like this. If there's a lot of it to begin in, we'll start way up there. If there's not very much to begin with, we'll start down closer to here. That, in essence, is what we were doing in those last two questions. Does that help? I have no idea, but it seemed like a good question. Okay. Having said that, we're now going to have a question that's completely different. This one, it may not be so obvious, not this one, but this one over here. It may not be so obvious that this is an exponential equation that we're after. So it says, I've got an interest in a bank account. It earns 35%, 0.35%, I should say, of interest per month, given an equation that models the amount of money in the account. Now, it's not obvious, I don't think, initially that it should be an exponential function that does this. But if I go through the logic, hopefully it will make some sense. So let me go through it. So let's set up a variable or two. So let AY, I don't know why, Y for years. That seems like a reasonable amount now that I think about it. Let AY be the amount of money, in the account after Y years. We know that when we set up the account, we put in $100,000. So we know that when Y is 0, the amount of money in the account is $100,000. What else do we know? We know that this thing earns 0.35% of interest per month. So at the end of 1 month, that amount of interest gets put in. So I can say that after 1/12 of a year, 1 month, the amount of money in that account will be the amount I deposited plus my interest. It's 0.35% of 100,000. So that's the deposit, and that's the interest. And this says after 1 month. That, I think, seems reasonable, yeah? Yep. Now, sorry? It's 0.35%. Yeah, it's small. Yeah, yep. Now, for reasons that aren't necessarily clear for the minute, what I'm going to do is I'm going to take out these 100,000s as a common factor in here. So I could actually work that number out, but I don't want to. I want to leave that as 100,000 times 1 plus 0.0035, which I will write as 1.0035 times 100,000. Now, as I say, I could work that out, but for the moment, it's better if I leave it like that. So that's how much money is in the account after 1 month. At the end of the next month, we get some more interest. So after 2 months, I have the amount of money that's in there, 1.0035 times 100,000. So that's the amount that money's in there, plus the interest on that. Having written it that way, I can see that 1.0035 times 100,000 now is common. So I can take that out as a common factor, times 100,000. And then I have 1 plus 0.0035. That number is just 1.0035. So this whole thing simplifies to be 1.0035 to the power 2 times 100,000. And you say, so what? And I say, if I were to do that one more time, I won't go through the details, you'll just trust me that I get it right. But after 3 months, this comes out to be 1.0035 cubed times 100,000. And we can start to see the pattern. At the end of each month, at the end of the second month it's squared, at the end of the third month it's cubed, and so forth. So after n months, so if I can go down here, I could say A, n on 12 will be 1.0035 to the n times 100,000 in there. And now I'm getting something that looks very much like an exponential function. Now, I didn't want to work here. N is, in fact, the number of months. That's the number of months. I actually want this thing in years. And so every 12 months is 1 year. So I'll say but y is equal to n on 12. 12 months gives me 1 year, 24 months gives me 2 years, and so forth. Or if I like, n is equal to 12y, I can say that ay, n on 12 is just y, is equal to 100,000 times 1.0035 to the 12y. And there would be an equation describing the amount of money in the account, and it's an exponential function. Here's my A, 100,000 in this case is your initial deposit, and here's your K12, don't know what that means, it's just 12. So as a result of those examples, you're supposed to be convinced that exponential functions are important. Okay?